Good morning. I'm Robert Kahn, the Senior Scientist Emeritus at Lawrence Berkeley National Laboratory. I'm very pleased to introduce our speaker for the last in the series of talks on the intangible universe. Professor Gabi Orebi-Gann joined the Berkeley faculty in 2012 after receiving her PhD from Oxford and holding a postdoctoral position at Penn. She's an expert in both neutrinos and dark matter. Today, she will talk about neutrinos. Neutrinos are the most enigmatic of the known particles. They were hypothesized by Wolfgang Pauli in 1930 and first detected in the 1950s, but we still don't know all their properties. According to popular theories, they are the reason there is any tangible substance in the universe, even though they themselves are intangible. Professor Orebi-Gann will tell us what we know about neutrinos, what we don't know, and how we're trying to change that.
Thank you very much for that very nice introduction, Bob. Let me share my screen. Okay, hopefully everyone can see that okay?
Yes.
Great. So as Bob mentioned, I will be talking about unlocking the secrets of the universe with neutrinos. And it's a great pleasure to be here. And I look forward to a lively discussion. So just to give you an idea of what I'm going to talk about, I'm actually going to start in the field of stellar astrophysics and how the sun relates to neutrinos. So I'll then step back and talk a little bit about neutrinos as nature's messenger. This is one of the terms by which they tend to be known because we can use neutrinos really to probe the world around us. And then I'll talk a little bit about novel technology development that will actually allow us to move into a new regime of sensitivity where we can really understand both the neutrino and use the neutrino to understand other fundamental questions. So let's start with understanding a little bit about neutrinos. And as I said, we'll start this story actually where my own relationship with neutrinos began, which is deep in the core of the sun. So we know that the sun is powered by nuclear fusion. Hydrogen in the intense heat and pressure in the core of the sun is fused into helium, and that releases a lot of energy. That's the heat and the light that we see. And it also produces as a byproduct a lot of neutrinos, billions of neutrinos every second. And actually the motivation for looking for those neutrinos originally was to confirm our understanding of how the sun is powered. So back in the 60s, a number of experiments sought to detect the neutrinos that were produced in the sun in order to confirm our understanding of stellar astrophysics. So let's talk a little bit more about the neutrinos. They are tiny fundamental particles. As I mentioned, the sun produces billions, and actually there are 70 billion neutrinos passing through your thumbnail every second, just from the sun. Originally, they were thought to be massless. Now we know better. But they're produced as products of nuclear reactions, such as the fusion in the sun, but also fission reactions that power nuclear reactors, particle decay, for example, cosmogenic particles in the atmosphere. And we can also produce man-made beams of neutrinos. Because they are so very light, as Bob said, intangible, they travel close to the speed of light, effectively at the speed of light. So they can travel between the sun and the earth in 8 minutes. Now, one of the reasons that neutrinos are so useful to us is because they interact very weakly. So actually, the neutrinos that we detect from the sun, they were produced in the core about 8 minutes ago. That is actually the closest thing we have to a real-time monitor of the sun, because the light that we see was actually produced thousands of years ago. Because in order to travel out from the core of the sun, it goes through many interactions on its way out. Whereas the neutrinos, once they're produced, they just shoot straight out. So they give us a way to monitor the sun in real time. I mentioned how weakly interacting they are. A light year of lead would stop about 50% of a beam of neutrinos. So you've got like a 50-50 chance of stopping a neutrino. If you put a light year of lead in its path, they can just travel straight through, which is quite astonishing. And because of that, we need huge detectors and, importantly, high intensity sources of neutrinos in order to have any chance of seeing them. So obviously I'm using the sun as a backdrop here. This should be a familiar image. This is the sun imaged in neutrinos. So when you detect a neutrino, you can actually, depending on how you detect it, you can detect the direction from which it came, which means you can use the neutrinos from the sun to sort of map out an image of the sun. And that's what you're seeing here. So I talked about the experiments that sought to measure the flux of neutrinos from the sun. And there were a few of them. Hopefully you can see my mouse. So these blue points on the figure, these are the results of experiments measuring the flux of neutrinos produced in the sun. And the black points along the top, these are the theoretical prediction based on our best understanding at the time of the nuclear fusion reactions that power the sun. And you can see there is quite a significant discrepancy. So the y-axis here is just the ratio to SSM is standard solar model. So it's just the ratio to the prediction, which is why all the predictions sit at exactly 1. And you see that the experiments clearly saw a deficit. They're not seeing as many neutrinos produced in the sun as we expected. And this became a mystery for several decades. It was called the solar neutrino problem. And there were many theories put forward as to what could be going on. Maybe we don't understand the sun. Maybe we don't understand neutrinos, or maybe there's something wrong with the experiments, that they're not measuring what we think they're measuring in some way. In order to resolve this, a new experiment was proposed, and this is actually the experiment on which I did my thesis at Oxford, as Bob mentioned. This experiment was called the Sudbury Neutrino Observatory, and it was a 12-meter diameter acrylic vessel. So you see that sitting here on the left. This is basically a giant plastic ball that was filled with heavy water and surrounded by nearly 10,000 photon detectors. So each of these little circles that you can see around the outside, each one of these is a photon detector that can detect light that is produced by the neutrino interactions in this target, inside the target vessel. So the reason for this experiment is one of the theories for what was going on with solar neutrinos is something to do with the neutrino behavior, and in particular neutrino flavor. So there are actually 3 different, we call them flavors of neutrinos, 3 different types of neutrinos. And they partner each of the charged leptons that we know about, the electron, the muon, and the tau. And we do know that all of the neutrinos produced in the sun, if we understand the processes correctly, should be produced as electron neutrinos. Now, the experiments that had been designed to date, they had measured the flux of neutrinos via interactions that were only or primarily sensitive to electron neutrinos. One of those ways, just to give an example, is a large experiment called, in its initial phase, Kamiokande, and then the next generation was called Super Kamiokande, which again was a huge vat of water. So I mentioned you need very big detectors to see neutrinos, and that was a 50 kiloton vat of water. That's about maybe 25 meters, a right cylinder. And in that kind of detector, neutrinos are detected just by scattering. So the neutrino will travel from the sun to the detector and scatter an electron in the detector. And that electron is given enough energy from that scatter that it can actually produce light, and you detect that light. So the Sudbury Neutrino Observatory is based around the same idea, but because of having heavy water is the same as regular water, but there's an extra neutron in the nucleus, and that allows a couple of additional ways to detect the neutrinos. So one of those ways is where the neutrino comes in, scatters the nucleus. Instead of scattering an electron, it scatters the nucleus and it breaks it apart. So the proton and the neutron are broken away from each other, and the neutrino goes on its way. But you can detect the products of that scatter. That's called the neutral current interaction. And that interaction does not depend on the flavor. So Sudbury Neutrino Observatory, or SNO, was able to measure the total flux of neutrinos independent of this flavor. And then they also had another channel for interaction that really was sensitive only to electron neutrinos. And it's that capability that allowed SNO to resolve the solid neutrino problem, because that flavor blind measurement agreed beautifully with prediction. And the measurement that's just sensitive to electron flavor agreed well with other experiments. And so what that told us is that the electron neutrinos produced in the sun are changing flavor. They're changing their nature before we detect them on Earth. That was a huge leap in our understanding, and it earned the director of SNO a share in the 2015 Nobel Prize. And then at the same time, the fact that this flavor blind neutral current measurement agreed with the prediction, this is actually very reassuring, because it tells us we do understand how the sun works. Given our heavy dependence on that body, that's quite important. So this really contributed to our understanding of neutrinos. And this figure, it looks a little bit complicated, but don't be put off by it. This is describing what we call the standard model of particle physics. So there's a number of fundamental particles that we know about that make up matter. And we divide them into these three generations, where they have the particles in each generation have similar properties to each other, but with increasing generation, they actually have increasing mass. And the neutrinos sit here as partners to the charged lepton. So you're probably all familiar with the electron, and there is an electron neutrino that interacts with the electron. And then there's a muon neutrino to partner the muon, and a tau neutrino to partner the tau. So as we said, some of the properties we know about neutrinos, they interact very, very weakly. They have very tiny masses, originally thought to be massless, and they do come in three flavors as far as we know. So you can verify how many neutrino flavors there are by looking at collider experiments, which produce some of the bosons that actually mediate the interaction between particles. For example, the Z boson. The Z boson is a particle that mediates the interaction, for example, between the electron and the electron neutrino. And if you look at the width of the Z boson, that width is defined by how many different particles it can decay into. And it should be able to decay into all of the neutrinos, and it's consistent with there being three neutrinos. So you can see in this figure the different lines, the different line styles for the hypothesis that there might be 2, 3, or 4 neutrinos, and all of the data sits very nicely consistent with there being 3. Now, there's a couple of caveats to that, which if you're interested in that, do ask me about it later. So the discovery at Sudbury Neutrino Observatory really was one of two major pieces of evidence that informed our understanding of a phenomenon called neutrino oscillation. So I've talked about these weak states, the flavor states of neutrinos, the electron, muon, and tau. And those are the states in which neutrinos are produced, but we actually now understand they propagate in a different set of states. They're physical or mass states, and physicists being as creative as we are, those are just called 1, 2, and 3. And it's easier to think about if we just simplify the picture. If we pretend there are just 2 neutrinos, we can think about the picture this way. So the 1 and 2 state, those are the pure states. And the electron and the muon state, those are actually a mixture of those two. So you can sort of think about it as a rotation. If your new 1 and your new 2 state are your orthogonal axes, if you rotate those axes a little bit, you get an electron neutrino and a muon neutrino. And the electron neutrino is mostly nu1 state, but it's got a little bit of nu2. And the amount it's got of nu2 is defined by how much you've rotated it away from nu1, nu2. So you can define it by this angle theta, which we call the mixing angle. That essentially tells you how the states, how much admixture you have of the two state in the electron flavor. And what this means is if you produce a neutrino in the electron state, it's sort of made up of some fraction of 1 and some fraction of 2. And then when it propagates, those propagate with a phase difference, which means that if you measure that neutrino sometime later, it might not look like an electron neutrino anymore. The relative contributions of 1 and 2 will have changed, and it might look more like a muon neutrino, depending on how far it has traveled and depending on the energy of the neutrino. And that's this phenomenon called neutrino oscillation, that although you produce an electron neutrino, when you detect it after some distance, it may not be an electron neutrino anymore, which is sort of a mind-blowing thing, because you produce a particle, and without any other interference other than that particle traveling through, it can just be a vacuum. It can change its nature. It can change its state. And one of the critical things about that, so this is the formula for the probability that an electron neutrino might be detected as a different flavor. And you'll see this term in here that is a delta m squared. That delta m refers to the difference of the masses nu1 and nu2. So in order for this phenomenon to happen, those masses can't both be 0. Or this term would be 0 and there would be no oscillation effect. So the critical part of this discovery actually comes down to the fact that it requires neutrinos to have mass. Up until the discovery of neutrino oscillation, people understood that they were massless. So I'm getting a little bit of an echo. Is there a question? Okay. This is a slightly complicated concept to wrap one's head around, but I quite like the analogy to just a classical coupled oscillator. So you're probably all familiar with if you string two pendula from the same string, then they act as what's called a coupled oscillator. If you set one of them moving, so for example, you set the green one moving, over time, without you doing anything, the motion shifts to the red one and then back again. So that's similar. It's a close analogy to neutrino oscillation, where they're essentially coupled through the string in this case. And each pendulum is like the flavor state. So if you imagine the green pendulum is the electron neutrino and the red pendulum is the muon neutrino, if it starts as an electron neutrino, over time it can shift to a muon neutrino and then it shifts back again. And similarly to the coupled oscillator, if you started, I'm afraid I don't have a video of this, but if you started the two pendulum moving together, so they were swinging in phase, they stay moving like that essentially forever, barring, air resistance, they'll come to a stop, but the state is not going to change. They're going to move in the same, with the same relative motion. The same thing is true with the neutrino mass states. If you create a new one, it will remain as a new one. So that's called the normal mode. And it really is an exciting phenomenon, because we're seeing quantum oscillations. We're seeing the effect of quantum mechanics on a macroscopic scale, because these oscillations can happen over meters, kilometers, thousands of kilometers. And as I mentioned, that discovery earned the directors of Super Kamiokande, which I mentioned, and Snow, the 2015 Nobel Prize for the discovery of neutrino oscillations, which shows that neutrinos have mass. So let me step back and say a little bit about why neutrino physics is quite so difficult. I've talked about neutrinos being weakly interacting, but to give you a scale, this is a cartoon, not to scale. So neutrinos are produced in the sun, and they're detected on the Earth in a detector such as SNO. So snow is actually in a mine that's a couple of kilometers under the surface of the Earth, but effectively it's on this side of the Earth. And so during the daytime, snow is detecting neutrinos that have traveled through the vacuum of space. During the nighttime, you've of course put the entire span of the Earth essentially in the path of those neutrinos. And what is quite astonishing is snow sees just as many neutrinos during the nighttime as during the daytime. So what that's telling us is that you put the entire Earth in the path of the neutrinos, and they're just going straight through. Now, there is actually, we do expect to see some effect. The neutrinos should interact with the Earth just a little bit. It is just such a small effect that we don't yet have the precision with our detectors to see it. And I think that in itself just indicates why this field is quite so challenging. Okay, so I mentioned that neutrinos have this nickname as nature's messenger. So what am I talking about? And what are the interesting questions that are still out there to address with neutrinos? Because they are so weakly interacting, neutrinos provide a unique probe of otherwise unreachable regions. We can actually detect neutrinos produced inside the Earth. I've already mentioned produced inside the core of the sun, and produced in far distant supernova. And those neutrinos give us unique signatures to learn things that we have no other way to address. And I'll talk a little bit more about some of the questions that we can address there. And then also, the neutrino is a fascinating particle in its own right, and there are some fundamental questions that we still don't know. So I've said that neutrinos have mass. We know it's non-zero, but we don't know what it is. We know it's tiny, but we don't know the number. We actually don't even know which of the neutrinos is the heaviest. So that sounds kind of crazy. How can you not know that? But the reason is because the neutrino oscillation is sensitive to the magnitude of the mass difference, but not the sign. So we know that there's a mass difference between different states, but we actually don't know which one is heavier. And then we also don't have a full, we have first measurements of most of the mixing parameters. So I talked about the angle, the mixing angle that defines how much of the electron neutrino state, how much of the nu2 state is in the electron neutrino, for example. We've measured all of those parameters, but improved precision can tell us more about how the neutrinos behave. So that's some of the parameters that define their behavior. But I would say the most fundamental question and the most exciting question, we actually don't know the nature of the neutrino itself. The neutrino has a unique potential to be its own antiparticle. That's what we call a Majorana particle. And the reason for that is that it's actually the only known fermion, fundamental fermion, that is neutral. So if you think about the electron, it has an electric charge, a negative charge. Its antiparticle, the positron, has a positive charge. They're obviously different particles. They have different electric charge. What is it that fundamentally differentiates the neutrino from its antiparticle? There's something called lepton number, which we defined to help ourselves keep track when we're doing our calculations. But there's no particular reason as of yet for us to believe that that's some fundamental quantity. That's just bookkeeping, really. So I use this picture of Escher from Escher. I'm a big Escher fan. But I really like the way in this case, the birds traveling to the left are formed from the negative space of the birds traveling to the right. I think it's a really nice analogy for Majorana neutrinos, because we're talking about the neutrino being the inverse of itself, essentially. Another related question is whether neutrinos and antineutrinos behave in the same way. And these two questions together, I'm going to make a statement that will sound quite grandiose, could explain the origin of our matter-dominated universe. So that obviously is a sweeping statement. So I will explain that in a little bit more detail. So let's talk about matter and antimatter. Something called CP violation is a measure of the difference in the behavior of matter and antimatter. So for example, if you have a beam of neutrinos, let's say you have muon neutrinos, and you look for the probability that they change to electron neutrinos, then you can do the same thing for the anti-muon neutrino and look for the probability it changes to an anti-electron neutrino. And if those are different, that's CP violation. That's saying the neutrino and the antineutrino behave differently. Now, if we look around the universe, we see that matter far outweighs antimatter. Our universe is clearly dominated by matter. And that's kind of a good thing, because if there were equal amounts of the two, we know what happens when matter and antimatter come together, they annihilate. And so one might imagine if there were equal amounts of the two, eventually it all would have annihilated and we would not be sitting here. But where does this asymmetry come from? There must be CP violation to allow for matter to have somehow outpaced antimatter. Now, we have sought to measure CP violation, and a certain amount, a small amount, has been seen in the quark sector, the strong sector, but it's a very small amount, and it's not enough to anywhere near explain the degree of the asymmetry in the universe. If neutrinos exhibit CP violation, and if they are Majorana neutrinos, then there is a way to explain this asymmetry. So what happens is, if neutrinos are Majorana, they effectively split what we would call the sort of standard neutrino, the Dirac neutrino, which would be more similar to the other particles we understand. It gets split into two. One of those naturally becomes incredibly light. So this could explain why neutrinos are so much lighter than all of the other particles that we know about. But then it would have a sister particle that is incredibly heavy, heavy enough that it's made in the Big Bang. So very high energy scales. And if that sister particle exhibits CP violation in its decay, that could explain the current asymmetry. So the two ingredients we need are CP violation and Majorana neutrinos, which is when neutrinos are their own antiparticle. So how do we search for Majorana neutrinos? We do that looking at a certain kind of particle decay. So when a nucleus is unstable, it can decay. There's a number of different ways they can decay: beta decay, alpha decay, gamma decay. For a small number of nuclei in nature, the preferred mode of decay is something called, oh, I'm sorry. Are you still seeing the screen okay? My screen just flickered.
Yeah,
it's something called, it's okay?
Yes, it's okay.
Great. Sorry. I think I think I just had a power glitch. So for a small number of isotopes in nature, the preferred mode of decay is something called 2-neutrino double beta decay. Now, we're familiar with the process of beta decay, which is where a neutron in a nucleus will decay into a proton and release an electron and an electron neutrino, actually an antineutrino. For some nuclei where that is just not energetically favored, what happens is effectively two neutrons undergo that process simultaneously. It's a coupled process, so they're happening at the same time, and you get two electrons and two neutrinos. If the neutrino is its own antiparticle, they can effectively annihilate inside the nucleus, and the only thing released is the electron pair. And that process, that's called neutrino-less double beta decay, because you're not getting any neutrinos. And if we see that process, that tells us that neutrinos must be Majorana in nature. So you'll see I've put some numbers underneath each of these. These are half-lives for this process. So that's telling us, if you have, one atom, what is the time frame over which it's likely to actually exhibit this process? And right now, for the small number of isotopes known to undergo the 2-neutrino process, we have looked for this neutrino-less process, and the limits on half-lives are on the order of 10 to the 26 years. That's a really big number For scale, the age of the universe is 10 to the 10 years. So this is a huge number. But fortunately, Avogadro's number is also a large number. What that means is if you have a mole of an isotope, which is maybe just a few kilograms of an isotope, you actually have a vast number of nuclei, and you have some chance of actually seeing this process. And again, if you see this process, that tells you that lepton number is not conserved, that neutrinos must have a Majorana nature. And actually, interestingly, the rate of this process gives us a measure of the neutrino mass. And this is one of the highest priorities in nuclear physics in the US at the moment, is searching for this process because of the impact it could have on our understanding. So how do we search for this process? It's incredibly challenging. So this figure shows the signature in blue for that 2 neutrino decay. And what you're measuring is the energy of the outgoing electrons. So if the 2 neutrinos escape, the reason you get this continuous spectrum is because the neutrinos can take any fraction of the energy of the decay. If the neutrinos do not escape, the electrons carry all the energy, and you get the energy of those electrons will sit right here at the endpoint because they're carrying all the energy of the decay. So what we are searching for is a little peak at the endpoint of this big spectrum. And that's an incredibly challenging thing to search for because you're searching for a very small, this is exaggerated already, you're searching for a very small signature next to a known, what is effectively a very large background, right next to where you're looking. So you need very good energy resolution. You need a large mass of your target material to have any chance of seeing it. And you need very, very low background. You need there to be nothing else in your detector that can mimic the signature of the events here. So it's very challenging, but it's very exciting because it really is a fork in the road. If neutrinos are Majorana in nature, this is new physics. These are the first particles the first fermions that have this property, and it means they don't get mass the same way other particles get mass. It means they behave differently from all of the other particles. That's very exciting. If they're not Majorana, there's still new physics because it means we don't understand what it is that differentiates the neutrino from the antineutrino. There's some other fundamental symmetry that defines that difference that we don't understand. So it's really exciting either way. And those are the best questions. So, whatever the answer is, it's exciting and new. So one of the ways that we are looking for this process is using liquid scintillator experiments. So I talked about the Sudbury Neutrino Observatory, which was filled with heavy water. And here's that detector again, here in the center. A collaboration called SNOW+ has taken that detector, reusing the detector, which is located, I mentioned briefly, deep in a mine. It's actually 2 kilometers underground. This shows a schematic of the mine in an active nickel mine in northern Ontario, a place called Sudbury. And this figure here shows a schematic of the underground lab that has been built up around that original SNOW experiment. So here is the cavern where SNOW is located. And remember, this acrylic ball is 12 meters across. So you've got some idea for the scale of this lab. It's a vast underground laboratory hosting a number of experiments. And SNOW+, what we are doing is filling this detector, instead of having it filled with water, we fill it with something called liquid scintillator. And this is a liquid that, when a neutrino interacts, produces vastly more light than you get in water, which means you get a much better measure of the energy of the neutrino interaction. And if you then load that scintillator with one of these isotopes known to undergo this 2 neutrino decay, you can search for the neutrinoless process, and you get very good sensitivity to search for Majorana neutrinos. And the isotope we will use is tellurium-130. So just to give you an idea of where SNOW is located, this here is shaft number 9 at the Ole Inco mine. And when you're going underground to SNOW Lab, you go, you get into essentially it's called the cage, which is a metal box. and you rattle down 6,800 feet down this rock shaft in order to get to the mining tunnels on the 6,800-foot level, where when you come out of the cage, you hike through about 2 kilometers of mining tunnels that are used as part of this active mine. It's dark. There's often maybe a foot of water underground, on the ground. And there's multiple routes, so you have to be sure you're going with someone who knows the way, so you don't get lost underground. But assuming you go the right way, eventually there is a light at the end of the tunnel, quite literally, as you approach Snow Lab. And Snow Lab, the entirety of Snow Lab is a clean environment, because I've talked about backgrounds being a concern, and there's all sorts of sources of backgrounds, particularly mine air is not clean at all. So the entire laboratory is a clean room environment. And when you enter, you have to go through a cleaning process yourself. So you're in your mining gear in order to have come down and hike through the drifts. All of that comes off. You go through showers and you get into the clean room gear, which is what you will spend your time in when you're at Snow Lab. So Snow Plus, this is an image taken from inside the detector. You can see here's that acrylic sphere. And this is actually filled, this image is while the detector is already filled with scintillator. That fill was completed about 2 years ago now, making Snow Plus the largest, deepest operating scintillator detector in the world. And it does have an incredibly low background, low enough that we've achieved the target background levels necessary to do the double beta decay search that we wish. And there is also a broad ongoing physics program, which I can also talk about if you're interested. But I would like to move on to some new technology that can really shed light on the future. And I realize I've been going for maybe about 35 minutes, so I'll just spend a few minutes here. But this for me, is really where the excitement is, because this is where the path forwards is. So we talked about what are Cherenkov detectors, and how these work is that when a neutrino scatters, for example, an electron, and that electron gets enough energy, it produces Cherenkov light, which you can think of Cherenkov light as sort of like a sonic boom, but in light. So it has the same cone-like topology. It's produced around the trajectory of the particle. And because of that cone-like topology, you can use it to understand the direction of the particle's travel, the trajectory of the particle. And that is really useful information. That, for example, you can use to point back and say, this neutrino came from the sun. The other kind of detector we talked about is scintillation detectors. And these produce light isotropically, but they produce a lot more light, maybe 50 times more light. And those additional photons are really important, because they give you a much better handle on the energy of the interaction and where the interaction took place. So depending what you're trying to achieve, you can do a Cherenkov detector or you can do a scintillation detector. Now, okay, I was never one for compromise. Why pick? Can't we do both in the same detector? If we have Cherenkov light, then we've got the directional sensitivity. And if we also have scintillation light, we've got the really good detector resolution. And actually, the whole is greater than the sum of the parts. If you really have both, the ratio of the two signals actually tells you about the kind of particle that's interacting, because an alpha particle and a beta particle will look very different in that ratio. And that capability for background rejection opens up a very broad physics program that you could do in a single detector. So that sounds really appealing. Why haven't people done it already? Because it's really hard. So this figure, this is kind of a cartoon that shows the photon intensity as a function of time. And here's the Cherenkov signature. So remember, that gives you your nice directionality. And here is the scintillation light. So this is a cartoon, but this little inset shows a slightly more realistic version. This is for a simulation of an actual detector. Here's the Cherenkov light, this little black thing here, and here's the scintillation. So what you see is the Cherenkov is a small signature that gets swamped under this very significant scintillation peak. And what we want to do is pick out that Cherenkov signature without losing the scintillation. And there's a number of ways you can do that. You can use the fact that the Cherenkov light has this cone-like topology to identify light that is produced in that ring on top of the flat isotropic scintillation. You can also use timing. The Cherenkov light is produced essentially immediately when the particle interacts, whereas scintillation light has a time profile to it. There's both a rise time and a decay time, and actually you can essentially custom make your scintillator to define that time profile. So you can actually delay the scintillation, or you can use very fast photon detectors, an example of which is shown here, to separate the two signatures. Or, and this one's really cool, you can actually use wavelength. Scintillation tends to be narrow band in the blue, and Cherenkov is a very broad spectrum. So you can actually separate with wavelength. You can have a regime where you're just getting scintillation light, and then a regime where you're detecting Cherenkov light. And what we seek to do is combine all of these technologies in a single cutting edge detector in order to have good sensitivity, both to Cherenkov and scintillation. And that detector is a large experiment that we would like to build called THEIA. Now, THEIA is named for the Titan goddess of light. That's the picture on the left there. I'm showing it around the Statue of Liberty just to give you an idea of the scale of detector that we would like to build. This is roughly to scale in our ideal case, what we would build. But we were not the first to take this goddess's name in vain. If you Google THEIA, the first thing that comes up actually is a fashion designer. And that sponsorship deal is under negotiation. So with THEIA, what we would like to do is essentially achieve a 2-for-1 kind of deal, 2 detectors in one. What you're seeing here is an image of an event. In this case, it's a high energy muon in the THEIA detector, where on the left, well, each of the colored dots represents a photon detector that has detected light. And on the left, we're reading out the channels that are sensitive to Cherenkov light. And you get a beautiful Cherenkov ring. That tells you that you're preserving the Cherenkov signature. And on the right, we're reading out the channels sensitive to scintillation, and you get a lot of light. So that's the benefit of scintillation. You get a lot of light, which gives you a lot of information about the energy and position of the event. And here you can see the entrance and the exit wound of the muon very clearly in the color shows the intensity of the light, the more intense light. So let me just step back for a second, because I talked about Majorana neutrinos, but I didn't talk about how we measure CP violation. And that is done by producing a high energy beam of neutrinos, which will be produced at Fermi Lab in Illinois, and pointing them through the crust of the Earth, in this case, 800 miles, to a detector where you then measure them. And the beam, this man-made beam, can be run either producing neutrinos or producing antineutrinos. So you run for a few years in each mode, and you look at what you see in the far detector and you compare them. And you say, are the neutrinos behaving in the same way as the antineutrinos? And if they're not, that's CP violation. And there is a detector, an experiment being designed called the Deep Underground Neutrino Experiment, or DUNE, to do exactly this. It will have a beam at Fermi Lab and far detectors positioned here at the Sanford Underground Research Facility in South Dakota to detect that beam. Now, DUNE's primary goal is to measure CP violation. And it has some additional physics that it can do as well, primarily supernova physics. And it's actually proceeding in 2 phases. In the first phase, 2 smaller detectors will be built at that far site using liquid argon technology. And in the second phase, 2 additional detectors will be built that could use other technology. And we see THEIA, this Cherenkov scintillation detection, as being one of those additional far detectors. And so it would give you a broad low energy program but it would also give you sensitivity to CP violation by detecting neutrinos from this beam. And I realize that I'm getting a little close on time. I've got a few slides on the physics program that you could do with this detector, but maybe what I can do is I can skip the details and we can talk about them in the discussion if we want to, and I could just summarize that program. So, I mean, the bottom line is that in a single detector, in this THEIA detector, we could use neutrinos to probe nature. We could detect solar neutrinos, supernova neutrinos, geoneutrinos produced inside the Earth. But we can also study the fundamental nature of matter. In this single detector, we would have world-leading sensitivity to the search for Majorana neutrinos and also to the search for CP violation in a single detector. So we're doing particle astrophysics, we're doing nuclear physics, we're doing high energy physics. This spans 5 orders of magnitude in energy. And in one detector, you could show that neutrinos and antineutrinos are the same by detecting Majorana neutrinos. And you could demonstrate that neutrinos and antineutrinos oscillate differently by seeing CP violation. And those are the 2 ingredients that could explain the origin of our matter-dominated universe. So I had a little bit more detail on the physics. I'm going to skip through that detail, just because I want to say that this is a really exciting physics program. And what we need to do to get there is demonstrate the technology. So right now, literally this summer here at Berkeley, we will be building a demonstrator called EOS. EOS is the Titan goddess of dawn and Theia's daughter in the pantheon of gods. And we will demonstrate all of these technologies in an integrated way. So EOS will be a steel outer tank with an acrylic inner vessel that will be filled with the novel scintillator, surrounded by fast cutting-edge photon detectors. And at the bottom, we will have spectrally sensitive photon detectors that allow us to do this spectral separation. So we will fully characterize the ability to differentiate different particle types using this combined Cherenkov and scintillation signature in this detector. And it's a very exciting time because these images show different pieces of the detector that are being manufactured as we speak. This is the acrylic tank here. This is that same tank, but wrapped in light protecting film. And this is the space on campus where ultimately we will assemble the detector on this stand, and then we will have our final built detector sitting here. This is a basement in the nuclear engineering department. So this is a really exciting time because this technology development is happening now, and it's happening here at Berkeley. So I do just want to say a thank you to the team that's working on EOS. It's a broad international team. We actually have our biannual team meeting next week, hosted at Brookhaven, so I'll be flying out on Monday morning. And I also want to acknowledge the THEIA Collaboration, which is a also broad international collaboration of people who are really invested in this program. So let me summarize here, and then we can maybe have some discussion. Really just to say, neutrinos offer the potential to probe the universe around us. And we've had several decades of successful experiments that demonstrate a strong history of discovery, and the novel technology that we are developing offers a broad program of compelling science moving forwards, including insights into the mysteries of the universe and the fundamental properties of neutrinos themselves. So THEIA would be a powerful instrument of discovery across this broad range of physics, and EOS is a performance demonstrator that will demonstrate the capabilities we need to move ahead with a project like THEIA. So thank you very much.
Thanks, Gabi, for a fantastic presentation. I want to thank her again for a fantastic talk. This was really fun.
I very much enjoyed it. Thank you very much for the invitation.